This is the 36th lecture of the course MTH 204A for section B. Recall that for any group G and any representation where V is a vector space over some field, some F is an arbitrary field. Recall that for any representation rho of G on V, and let this be another and consider also another representation. So, for a given group G, not necessarily finite, but the at least now, and any vector space and vector spaces over some field F, if and two given representations, assume them irreducible. Okay. Then Schur's lemma says the following. So, Schur's lemma says that if rho is non-isomorphic to phi, then this set of all G invariant linear maps from V to W. Recall that by a G invariant linear map, I mean a linear map from V to W such that this diagram commutes for every G in G. Okay. So, Schur's lemma says that if the representations, both these irreducible representations are non-isomorphic, then this is trivial. So, this is the non-isomorphic part of Schur's lemma. In the second part, here we indeed we let us assume something. So, now we assume that F is C and dimension of V and W are finite. That is, so in this situation, let us F is C and we assume phi equal to rho. So, therefore, we are and of course and the dimension of V is finite. So, in this situation, this home G V W is isomorphic to C. Okay. So, to be somewhat more concrete, if T from V to V is G invariant, then T must be of this form for some lambda in C. Okay. This is what we so here also for none of these two statements we need finiteness of G. For the second part, we just need the field to be something algebraically closed field, namely this C and namely this C. Okay, so when V equal to W, we usually write it as end V, endomorphism. Okay, yeah. So, this is what Schur's lemma says. Now, as a corollary to Schur's lemma, we obtain the following. So, in the first case, that is when rho is not isomorphic to phi for any linear T from V to W, any linear map, what we do is, okay. So, here assuming G finite, now we assume G finite, we obtain the following. So, what we have to do is phi. Okay. So, this is simply 0 in the first case, because this operator is this is a G invariant linear operator, and by Schur's lemma it has to be the trivial operator. And in the second case, so all this we have seen earlier. In the second case, namely when we are working with when our field is algebraically closed, the dimension and both the representations are, they coincide, and the dimension is finite, and of course G, and now we also assume G is finite. In the second case, we must have, so here phi equal to rho, so it will be rho G inverse tau or T rho G. This is going to be lambda times I, and this lambda, where one can also compute lambda in terms of T, where lambda is, if you take the trace of both the sides, you will see that lambda into dimension of V becomes trace of T, because here we are basically they are being conjugated. So therefore, for their trace will be the trace of T. I mean, if you fix an ordered basis B of V, the trace of T is same as this trace of this operator, because this inverse they are inverse to each other. So therefore, lambda will be 1 by dimension V. So let us call it n time 1 by dimension V times trace of T. So this is what we have seen earlier. Now we are going to deduce some consequences from this. So we should do one by one. So here now onwards we throughout assume G is finite. Throughout we assume G is finite. Remember, in the Schur's lemma we do not need that. Throughout we assume G is finite, and since also now we assume both V and W are finite dimensional. Again, in this case it was not necessary, but we are now restricting ourselves to this situation, and M. Okay. So fix ordered basis B and B prime of V and W respectively Okay. So therefore we have the following, that for any G okay, here we have here we have beta prime. Now we concentrate to this case. So this is the rho g t phi g inverse. So this is basically rho g t phi g inverse is an operator from V to W, right? Because first rho g t and then phi g inverse. So this is an operator from, for any G, phi g inverse t rho g is an operator from V to W. We will and so is their sum. So this entire thing is an operator from V to W. Okay. Since this operator is 0, that means, so if we look at the matrix representation of this operator with respect to this ordered basis, relative to this ordered basis B and B prime, then all the matrix coefficients will be 0. Okay. we are now going to compute the matrix coefficients, and that will give us something very much that will have very important consequences. So, like here let me write it. So, T is from V, so we denote the matrix or like Ij as expected, I from 1 up to n and j from 1 up to n. Okay. This is what we have, and then okay. So let me first do it. So this for any alpha and beta. So alpha and beta are positive integers. So the, if you look at the right hand side, the entry of the matrix at the alpha, at the position, I mean alpha row and beta column will be the sum of the entries of the alpha beta position for each of the matrix, each of the matrices that come from this operator. So let me put it in this way, that so like here you have sum of operators. So if we look at the like matrix coefficients, okay, so this is my operator. Of course, that is going to be, if we can disregard this part, disregard this part, right. The matrix representation of the sum will be the sum of the matrix representations, and then we also have to observe something, that is like here so what do we have actually here? If you recall this commutative diagram, then we must observe this matrix representation has to be this, B prime followed by B prime, B prime, right. This is going to be the matrix representation. So therefore the alpha b, so the entry at the alpha comma beta position of the left hand side will be the sum of the entries of that position for sum of the entries of the entries at that position of all, so of all these summands, right. Okay. So therefore what we do is we will compute the entry at the alpha beta position for each of these summands, and their sum is going to be the entry at the alpha beta entry at the position alpha comma beta for this left hand side. So therefore we are now going to make that computation. So the computation is not complicated, however it looks somewhat messy, but again it is not difficult. So like fixed, now so from now onwards, I mean since I have already fixed and a set of ordered bases, so all the matrices that we are going to talk about with respect to that ordered basis only. So let we denote the coefficients of this. So here you see so alpha anyway. So this is So this is going to be a matrix, an n by n matrix. Okay. So R this and Ij, I and j both are from this matrix. So for the reason for writing G here is for each G will have a different matrix. The order bases are same, but the matrix will be different. The coefficients will depend upon G. So you can regard the coefficients as functions of G, and similarly, so this is also we will and let's say, I mean, the index is something. So this is a matrix, this is a m by m matrix. Okay. And I have already T is determined by this. So therefore now we are ready to compute. So the entry at the alpha beta position. So let me write down the matrix. So what we regard this is, so these are just now matrix products. So the alpha beta entry at the alpha comma beta position for a typical summand is going to be the product of the so it is going to be the inner product or whatever. It originates from the alpha-th row of this together with the beta-th column of this product, right. So keeping that in mind, what we do is, so we will explicitly make the computation. So let us say for a typical G, so the alpha-th row here is according to our notation, it is defined as G inverse alpha 2 alpha m. It is a m by m matrix, okay, where alpha is to m, and now we have to get the beta-th column of this product. Let us also compute that. So this matrix is basically according to our notation x1n, xm1, xm2, xmn, and then we have this. So it is the beta-th column here. So Rg 1 beta, Rg 2 beta, Rg n beta, right? Yeah. Rg, so n beta. Okay. And the columns are like this. So therefore, let us keep it like this, and then from the product of these two we can immediately compute the j beta-th column of this product. So how is that formed? So this is the beta-th column with this. So with this entry we multiply the first row, then the second entry we multiply the second column. So this one, so we multiply the first column by this, the second column by this, and then similarly the nth column by this, and then we take their sum. So therefore the j beta-th column of this matrix is certainly going to be the following object: Rg 1 comma beta x11 plus Rg 1 comma beta, sorry 2 comma beta x12 plus Rg n comma beta x1n. Similarly, this one here Rg 1 comma beta of xm1, Rg 2 comma beta xm2, so on and so forth, Rg n comma beta x n xmn. Okay. So this is going to be the jth beta-th column of this matrix. Okay. and now the entry at the alpha beta position of this matrix corresponding to this the arbitrary corresponding to this G will be simply this will, so this S G inverse alpha 1 will be so basically what we will do is let me write that is better. So as I have said that let me rather write this using summation, that will perhaps make it easier to see. So how should I do? Basically here what should be the index 1 up to n, alright. So here beta seems to be fixed. So Rg, should I write like this, Rg delta beta x delta Rg delta beta x, okay, no, just a minute. So this is moving, okay, x1 delta, maybe that is correct, 1 1 1 to 1 n, yeah. So delta from 1 up to n, right, Rg delta beta, yeah, then this is from delta is to 2 beta 1 2, okay, and this one is going to be similarly Rg delta beta x m delta runs over 1 up to n. So this is the jth column of this matrix, and now that is going to be multiplied by this alpha 1 Sg inverse alpha 2 Sg inverse alpha m, okay, right. So now we will simply compute that. Hopefully I haven't made any mistake. So what is going to be that? Sg inverse alpha 1 times n R G delta beta x 1 delta. So therefore what we can do is, okay, so maybe I should do so, okay. So here a typical element will be alpha gamma, and gamma will run from 1 up to m, okay, and this is simply a case of double summation in Sg inverse alpha gamma Rg delta beta times x. Okay, so here a typical term will be, yeah, so this gamma delta, yeah, here that the gamma position will be gamma delta, yes. So this is going to be the coefficient at the alpha beta position of this summand. Therefore the coefficient at the alpha beta position on the coefficient the alpha beta at the position alpha comma beta and the coefficient at that position. So again let me repeat, this is the coefficient at that position for any typical G. So the coefficient and the entire sum would be just the sum of this. So therefore I should write it, the coefficient at the alpha beta position, this matrix coefficient of the left hand side will be simply gamma from 1 up to m, delta from 1 up to n, then this fellow G in G S G inverse alpha gamma and Rg delta beta times as expected x gamma delta. Okay. Thus we have computed the explicitly the coefficient of this matrix at any given position alpha comma beta. Okay. All right. And as we have assumed the case that will be now working with the first case we are dealing with, that is here the assumption is rho is not isomorphic to phi. So therefore for any alpha comma beta this quantity is going to be 0, right. So try to understand, this is very crucial, that given this scenario, that is G is finite, two representation which are irreducible and non-isomorphic, given their dimensions are n and m. Now whatever t, so and also we fix basis, ordered basis beta and beta prime. So given all this, now whatever t you choose, this quantity is going to be 0, right, which I have just erased. Phi g inverse t rho g. Okay. So this, since whatever t you choose, this quantity is going to be 0. So that means t is arbitrary. So you can consider any linear map t. So since you have a one-to-one correspondence between the linear maps and the m by n matrices, so therefore that if as t is arbitrary, this matrix, this xij's, they can also take any arbitrary value, right, because we do have a bijection between t's and this matrices. So since t is arbitrary, these are also arbitrary, and then finally you see that for any values of this xij's, this quantity is going to be 0. Like remember that, like given these representations, so given the representations, once I fix the ordered basis b and beta prime, so these are fixed quantities. Now it just says that for any value of x, x gamma delta, this is going to be 0. So what does that mean? This is a linear form in this xij's, right. So this is the linear form, vanishes for any value of xij. So that means each of these coefficients will vanish. So therefore we obtain that so for any alpha, so in the first scenario, that is when we are working with two non-isomorphic irreducible representations, for any alpha and beta, this quantity alpha gamma Rg delta beta is going to be 0 for all delta and gamma, for all gamma 1 up to m and delta from 1 up to n. This is what we get, because we are basically having a linear forms in these variables, and for any value of this variable the linear form is taking the value 0, so therefore the coefficients have to vanish. Okay. So this is what we obtain in the so this is the relation that we obtain, for the matrix coefficients that we obtain in case of two non-isomorphic irreducible representations. Okay. Now we are going to look at the corresponding, the counterpart for the second case, where we are working with the same representations. The field is complex, the group is finite. The group is finite has always been assumed. The field is complex, So, in that case what will happen is the following, that of course in that second case beta prime and beta will be same. So, then I should simply I should correct it here. So, we will have only beta prime. Okay, so let me erase that completely. So, here we will have only one ordered basis of V phi equal to rho, and as expected that there this RGs and SGs will be the same. Now like as earlier, for any linear map T, this is all what we are going to see. So, that means its corresponding counterpart here is going to be the following, that so here I cannot, so in case of isomorphic representations this is what we are going to have. So, this is the coefficient at the alpha beta part of the matrix representation of this, right. Okay. Now, on the other hand, so since this is just lambda times this identity, and lambda is 1 by n trace t. So, here lambda is 1 by n times trace t. So, like what will happen here is okay. So, this lambda times I lambda trace t. So, what is trace t? Trace t is simply, recall that we have T is this matrix, so trace T is simply the sum of the diagonal elements. So, therefore, if you wish we can say this will be x11 up to x1 xnn. Okay. So, therefore, so this is the alpha beta coefficient. So, now what we obtain from here is, if alpha not equal to beta, let me do it here, if alpha not equal to beta, since this is a diagonal matrix, so certainly this will be 0. Okay. Because this quantity is going to be a diagonal matrix. So, if alpha not equal to beta, this is going to be 0. So, now we consider the case when alpha equal to beta. So, in the scenario alpha equal to beta, we will show the alpha beta coefficient will be simply, so let me write it down here, that will also very concrete. Here it will be R G inverse, R G inverse alpha gamma R G delta B delta alpha. Okay. So, this is going to be the so then this x delta gamma. So, this is the entry at the alpha comma alpha position. Okay, alpha comma alpha position, and now you know that this entry has to be, because this is the diagonal matrix, in fact this scalar matrix. So, this has to be equal to x11 x n n. Okay, and this relation goes, as I said, this relation holds for any values of xij, because this holds for, so like for any given t we are going to have this relation. Let me simply write it here, 1 by n trace t times identity. So for any given t, this is what we are going to have. So t is arbitrary, that ensures these values of xij is arbitrary. So therefore for any values of xij, this is the relation that we are going to have. You see on the right hand side only these terms will be surviving, so the same has to happen in the left hand side. Therefore whenever like delta not equal to gamma not equal to delta, that coefficient again has to completely vanish. Okay. So therefore this 0 will be, like earlier of course when alpha not equal to beta that was 0, and even if alpha equal to beta, then if delta not equal to gamma, then also it is 0. So like our situation is, let me first also make it write it here. Okay, I think we can combine these two. So if one of these happens, either alpha not equal to beta or delta not equal to gamma, if one of these happens, then certainly this coefficient is going to be 0. So now we are only left with the case when gamma equal to delta. So for that particular term, gamma equal to delta, we will have gamma equal to delta here, just a minute, yeah, so 1 by n times. So this again I think I made no, sorry, this is not lambda, this is 1 by n. So here from the left hand side, this is the term corresponding delta gamma equal to delta, and we must have that from the right hand side as well. Okay, and this is for any values of this variable. So therefore if alpha therefore this becomes exactly 1 by n if alpha equal to beta and gamma equal to delta. Okay. So this is so these are thus we obtain the relations regarding this matrix coefficients. We deduce these relations which will be very very important for us, in what we are going to talk about in a minute. Okay. So these relations are obtained by computing the coefficients of the matrices explicitly. Now as I said, apparently it looks quite messy and it looks quite cumbersome and like it actually looks very dry, but however this is going to have important consequences which I am going to talk about. So before that, just note that we do have this kind of relations, but if you are working with non-isomorphic irreducible representations, then this is always 0. For isomorphic situation, only in this case it will survive, and that will be 1 by dimension of V, otherwise it is going to be 0. Now let us come to the main thing that we want to talk about using this, is called orthogonality relations for characters. So before that, let me remind you the definition of a character. So from now on we will always assume G is finite unless otherwise specified, and V is a vector space. So we also assume V is a complex vector space and finite dimensional. However, the definition of character that we are going to give, that definition, I mean, as long as the vector space is finite over any field, the definition goes. But I mean, like for in arbitrary fields, we are not bothered about for right now. So complex vector space and finite dimensional. Okay, and rho is a representation. So if rho is a representation of G on the vector space V, so from now on we will simply say V comma rho is a representation of, okay, and given a representation, its character, so its character is defined as, okay, for any G in G, So, this is just basically the trace of the corresponding linear operator, and in order to talk about the trace, you first have to fix an ordered basis, but it is independent of that. Okay. So, let me now talk about the very basic properties of characters. Very basic properties of characters. So, first of all, one thing is clear that chi of 1 is dimension V, because chi, okay. So, we given a representation like when there is no chance of confusion, we deliberately drop rho from the notation. So, given a representation rho of 1 is the identity operator on V. So, therefore, its trace has to be the dimension of V. This is quite obvious. The second one is actually slightly non-obvious, and and this is where we are using that our vector spaces is over C. So, for this chi g is nothing but chi g bar. Why is this true? Let me give you a quick argument. So, one thing is clear that the group is finite. So, therefore, this linear operator is going to be, as we have argued in one of the earlier lectures, this linear operator is of finite order, and then its matrix is going to be a finite order matrix over C, hence it is diagonalizable. So, therefore, if lambda 1 up to lambda n are the, if lambda, so therefore it is diagonalizable. So, okay. So, this is by choosing an appropriate basis, this is going to be the matrix of rho g, okay. So, that the trace will be this sum of the eigenvalues, because it is a diagonal operator, okay. So, this is going to be the matrix of rho g, and then by the product rule for matrices, the matrix of rho g inverse will be the inverse of this matrix, okay. So, the inverse of this matrix will be the same the diagonal matrix, where diagonal elements are replaced by their respective inverses. Now, you see, since rho g is a matrix of finite order, each, like earlier we have argued this, that each lambda I is some root of unity. So, this we have already argued, hence I am just quickly explaining instead of writing much. Root of unity. So, therefore, lambda I inverse, because these are, has to be lambda I, so is conjugate, right. The complex numbers having absolute value 1, their inverses are their conjugates. So, therefore, the matrix of rho inverse in that appropriate basis will be simply the diagonal matrix, or diagonal entries are lambda 1 conjugate up to lambda n conjugate, hence its trace is going to be whole conjugate of lambda 1 up to lambda n, that is the trace of rho g. So, therefore, what we have obtained is trace of rho g inverse is conjugate of trace of rho g, that is exactly that yields this formula. So, again let me repeat. So, earlier we have observed that with respect to some appropriate basis, we can obtain the matrix of rho g in this form, and where this diagonal element entries are going to be some roots of unity, and since the matrix is diagonal, its inverse is going to be again a diagonal matrix, where the diagonal elements are being replaced by their respective inverses. Now, since they are roots of unity, inverses are just their conjugates, hence from this the result will follow. So, this is one thing. Another one thing is again a immediate property of the trace, some, as I say, some basic properties of characters. So, let G and H in G chi G H G inverse is chi H. Why so? Basically this is the trace of rho G, rho H, rho G inverse. Okay. The trace of this, and once you represent everything, once you represent this, the matrix of this with respect to some with respect to some ordered basis, then it will be conjugate of the matrix with respect. So, let me do it here. For any basis B, this is going to be, so of course rho H will be there, beta, and the matrix representations of these two. So, the matrix representations of these two operators are going to be inverse to each other, because rho is a homomorphism. So, therefore, this is going to be some conjugate of this. So, it will have same trace as that of rho H. So, that is exactly produces this. Okay. What next? Let us now define, so I am not going to erase this because this is going to be important. So, let me define the direct sum of representations. So, though this definition works in generality, however, we will talk about its character. So, ultimately we will come down to the scenario of finite group, finite dimensional over C, but however, if you want to give the definition generality, that is fine. So, therefore, let G be any group, not necessarily finite, and V and W are representations. So, these are vector spaces over any field F, representations over any field F, I mean vector spaces, and we do suppose we do have representations of G, V rho and W phi. Recall that V direct sum W is basically the Cartesian product, and it is a vector space with respect to pointwise, componentwise addition and scalar multiplication. Okay. So, this is a vector space. So, basically as if you have already said on this on this Cartesian product, the natural vector space structure that we can put is customary to denote this by this symbol. All right. So, or if this bothers you, then for the time being we can write this. Okay. Now, what we do is like given a, so we talk about this another representation of G on V mod on this VW. So, we sent each G to, so rho G, phi G. So, this is a linear operator from this direct sum to this sending. Okay, this just the usual product of two linear operators, the Cartesian product, rho G of V, phi G of W. So, since things are being done component wise, so that is also going to be a representation of, that is also going to be a representation of G. This is also going to be a representation of G on this. And now assume that the group is finite and the vector spaces are complex of the thing, then of course we can simply ask about what about the character of this product. Well, so let me use the standard terminology. So, it is customary to denote this vector space by VW and denote this representation by this as well. So, then the question is what is the character of, so this representation we denote this by rho direct sum phi. What is the character of rho phi? In order to talk about the character, you first have to have a matrix representation. So, if you choose a basis, so an ordered basis of ordered basis of V, and if you take B prime an ordered basis of W, then like B, so like from this you can immediately construct an ordered basis of B comma W, right, ordered basis of this direction. So let me yeah, so given an ordered basis here, okay, so I think I should write this like this, V1 V2 Vn, and B prime is W1 up to Wn. Then we construct the following basis done in this manner, that Vn0 and so this is going to be an ordered basis of this direct sum, right? This is going to be an ordered basis of that, and yes, so then with respect to this ordered basis, what is going to be the matrix representation of the direct sum? What is going to be the matrix representation? You see that first of all this rho g V1 up to rho g Vn, and for all this you will have 0 in the second component. So basically the matrix representation of this direct sum with respect to the ordered basis is precisely, okay, is going to be the following: this block diagonal matrix, okay, this is what we are going to get. That is pretty simple, because in the first n vectors the second components will throughout be 0. So therefore we are going to get 0 here, because in this since these are 0, so we are going to thoroughly get 0 here. Similarly for the last m component we are going to get 0 here, okay. So that immediately shows that the character of this is going to be the sum of the characters, okay. So therefore for under the direct sum of representations, characters simply add up, and we do not have to stop with 2, we can continue that for any finite number of representations, okay. Another one thing which we have to so this is the fourth property in this list. Then let us talk about the fifth one. So the isomorphic representations have same character. So if rho is isomorphic to phi, we will show that. In fact later on we will show the converse is also true. So how? That is quite easy. So this is isomorphic, means there is a G invariant linear map. So this easily follows from this diagram. So G invariant isomorphism we do have okay. So this is phi. Therefore let's start with an ordered basis B here and consider its image. So this is the image of beta by T, right. So therefore since these are isomorphic, then we immediately see T equal to okay, maybe I should put it like this, phi g equal to first you go this, okay, T rho g T inverse, right, since this is an isomorphism. Therefore the matrix representation of phi g with respect to beta prime is going to be the matrix representation of this. So, thus you can immediately see rho G beta beta and rho G beta beta and then the matrix of, okay. So, first it goes here, okay. So, beta prime to beta, beta and beta prime, right. Now, you see, since beta prime is the image of beta, B prime is the image of B under T. So, this matrix representation is both these matrices are certainly going to be identity. So, therefore, this is what we obtain, and that immediately shows their characters are going to be same. So, the isomorphic representations, they are going to have the same characters, and therefore, in view of this, the following becomes very clear, that the following becomes very clear that if for a representation, if a representation V comma rho is the direct sum of some subrepresentations of the subrepresentations direct sum of some subrepresentations. So, what it means is on let us say Wi I from 1 up to k. So, what this means is, so each Wi is G invariant and V is the internal direct sum of this. So, I like to remind you that so this is equivalent to say several things. So, whenever we say, so this is equivalent to say the following things, that each V can be written uniquely as this, where each Wi is coming from Wi. So, this is one, this is, so this is the definition of saying whenever a vector space is the direct sum of its subspaces, and this is in fact equivalent to the following, that if we so abstractly construct this direct sum in this manner, then this map, so now this is a separate object, namely the n tuples from this to V. This map is an isomorphism, their sum, okay. So, V is the direct sum of the subspaces W1 up to Wk. That's exactly same as saying from this Cartesian, from this object, which is the Cartesian product, from this object, this natural summation map is isomorphism, okay. All right. So, if this is the case, if now assume that V is the direct sum of these representations, then one obtains the following, that the chi rho is the sum of the characters of the subrepresentations on Wi. On Wi, right? Because like earlier saying V is the direct sum of the subspaces, that is equivalent to saying the equivalent to saying this vector space constructed abstractly by means of Cartesian product, that is isomorphic to V by the very natural map, right. And when things are G invariant, so this direct sum representation, so when the things will be G invariant, then this is equivalent to saying this direct sum representation is isomorphic to the representation on V, and for the direct sum representation we know its character is going to be the sum of the individual characters, and this says that character rho is going to be the character sum of the characters corresponding to sub representations. Okay. So the main point is this, as I say, this external internal business. Since they are isomorphic by a very natural map, we don't care. So saying a vector space V is a direct sum of its subspaces, that is exactly same as saying if you construct the direct sum externally or abstractly, then that is named by means of Cartesian product, then that is going to be isomorphic to V by a very natural map. When everything is G invariant, then that natural isomorphism is also a G invariant isomorphism. So thus we obtain that the direct sum representation is isomorphic to the representation on the given representation rho on V. Now the rest is just the combination of 4 and 5. Okay, so therefore we see that if we can decompose a representation into several sub-representations, then that gives us a decomposition of its character. Okay. Now let us come to the main point, the orthogonality relations of the characters, which we will be, okay, so I think this we can remove, this we can remove safely. All right. So let G be, as I said, G is always assumed to be a finite group. So therefore the set of all functions, so we consider the CG, the group ring, for this consists of all functions from G to C, this function, all functions from G to C, and since like G is a finite group, so this is isomorphic to some C to the power, like if I denote this by let us say n. So this is a complex vector space, of course, isomorphic to C to the power n. Okay, this is after all a finite set. Then since this vector space is isomorphic to C to the power n, on C to the power n we do have a very natural inner product. So what do we do here is the very simple thing, right? We order the elements of G in this manner. We see that the ordering does not matter. So therefore whenever we are given a map, in CG, we send it to the corresponding tuple here. Okay. So since we do have a natural inner product here, then we can make this space equipped with a very natural inner product coming from this. So therefore what is going to be the inner product here? If we are given two functions phi and psi in CG, so then what should be the inner product? The inner product of phi and G, this should be like we send them inside C to the Cn and then we simply take their usual inner product in Cn. So therefore it will be psi G phi G, psi G bar, and of course psi G1, psi G1 that is to be there, but since we take the sum, we don't have to go by this, we don't have to write this. So this is that is how the natural inner product on this CG should be. So if we take the usual inner product on Cn and transfer it to CG, then that's how it should be. Okay. If we do that, that is how if we define transfer this usual inner product to here, then for any two functions phi and psi, this is what we should have, right. just a minute. And but here we will simply make a further scaling. So we will understand the meaning purpose of this scaling. So now we we define the new inner product on this space, on this CG, just the what it should be the usual one, but with a scalar. So this is how we are. So this is the usual inner product together with a scalar. So that makes CG an inner product space. So finite dimension inner product space. Okay. So now we will just finish with one thing, that so if you see that the way characters are defined, characters of G, they lie in CG. So now we are going to show the orthogonality relations for characters, that will show that if we take the characters for two non-isomorphic irreducible representations, they are going to be orthogonal. Okay. So let me directly prove this. With that I will finish. Yeah. So here I should be very quick. Phi and let us say chi and let us say psi are characters of non-isomorphic representations. Okay. Then we will look at their product. Product will be simply chi g. Okay, maybe I can do it in this way. Chi g, and what is chi g? If you remember, chi g will be simply like okay. So what is chi g? Chi g is simply if we take the usual notation. So therefore in the usual notation, psi g bar is has to be G inverse, and that has to be the sum of the diagonal elements. So S G inverse 1 1 up to S G inverse NN, if we borrow the usual earlier notation. So therefore from that you can immediately see the following, that 1 by order of G, in fact I should write it S G inverse 1 1. So this is now immediate. I can leave it as an exercise. So this is this times, and there if we use the RG11, RGNN, okay, and then followed by order of G. Now corresponding to each position, the entry, corresponding to each position, the summand would look like this, right? The summand would look like this. If you take some alpha beta here and some delta gamma alpha alpha here and some delta delta here, so it will look like this. Since they are non-isomorphic, in view of this matrix coefficients, this will be 0. Okay. So that just follows from here that each summand here will look like this, and then the counterpart when they are from isomorphic characters, they will be just this. Okay. So this is the non-isomorphic characters, not only they are different, they are in fact orthogonal. The second thing is, if we are dealing with characters up to isomorphic representations, so they have to be the same. So therefore the claim is, so all these are irreducible characters after all. Okay, irreducible characters. If chi is an irreducible character, then this is what we claim. Like that is again quite easy to see in view of this, because if you write like this, so there the summand will be, so this is quite, I would say, easy, Rg inverse 1 1 Rg inverse Nn times Rg, because that is how you deal with, right, this chi g inverse times chi g. So, Rg 1 1 Rg Nn. So, therefore, you see that only the product of this and this and then this and that, these terms will survive in view of this, and whenever they survive they will be exactly like they will be exactly I mean each of these terms will be just n, these terms will be 1 by n, and we have n many terms, so therefore it will be n. So again let me repeat that so the sum over g, if you take the terms from here and some other term there, then in view of this those sums are going to vanish. So therefore I mean taking the product of this and then summing it over z, that term will survive. Similarly the second term, third term, and whenever they survive these are going to be n, 1 by n, and we do have such n many terms, therefore it will be 1. So thus we have proved the orthogonal relations from characters, that if we take the irreducible characters, the set of all irreducible characters, that is a subset of Cg, and that is an orthogonal subset. Just write the set of collection of irreducible characters are orthogonal. Irreducible characters is orthogonal. Okay. In fact, orthonormal, not only orthogonal, it is orthonormal. If you take, it's orthonormal if you take any two distinct irreducible characters, I mean then they are going to be 0. Well, so right now should I write orthonormal, because the two different characters. Okay, so if something, well, anyway, right now I think one more thing I should say, that the two characters are same if and only the representations are non-isomorphic. So yeah, but this is what we obtained, that two irreducible characters, if we take two non-isomorphic irreducible characters, they are going to be orthogonal, and the norm of any irreducible character is 1. Anyway, so with that I will finish.